All right, here we go. Another little video about steel design. Um, Sorry for the delay. So hopefully you guys all watched that video to kind of get you in the mood for steel design. We're gonna try to watch a couple little highlights of that movie here in a few minutes, just to kind of point out some things that are worthy of noting, and then we'll dive into steel design. Now, this is a kind of precursor to the new stuff. We're finishing up the other stuff with the take-home exam that I'm going to give you this Thursday. I'm also going to try to put together some sort of review session for you. Maybe we'll do that during class time tomorrow, during my regular office hours, or I think that might be the best. And so stay tuned for some sort of a formal announcement there, right? During the office hours, pretty well attended. Lots of people had questions associated with the homework and stuff. Maybe we'll do that same sort of thing, but I'll have a little bit of prepared remarks about what to expect on the exam, and then answer any questions associated with that. So, yeah, again, stay tuned for an announcement there. So, the first thing about steel design, it is a completely different beast than doing concrete design, and that's why I wanted you to watch that video. And I think I could. Let's see if I am allowed to do this. Maybe I'll continue to record while we're playing a YouTube video. Looks like we can.
The flat bar pieces are
I
then
don't know if this
placed in a
works, so we'll
plate
see.
duplicator.
So I guess the whole point of this, right, is this what's different about steel design, right? Concrete, right? Oh crap. Oh, yeah, it's still recording. Concrete design, right? You get to pick the member sizes. You get to select how much steel you include in it, right? You're in charge of all aspects of the design. Whereas, in steel design, it's different. That's not what we get to do, right? All these members are pre-made. They get made in a factory. They get shipped to the site. They get fabricated, which is they get all the holes, put them in the welds and all that stuff in a factory a lot of times, and they get shipped to the site, right? So you can see that it's a completely different beast, right? And so this video was kind of just to get you in the mood for this type of design, right? And so it's getting a little dated, but has really cool music at the beginning to kind of get you real excited about concrete design. But I guess some of the keys here, right? Maybe I don't know, we necessarily need to watch the video here, but the idea is, right, you go through the design, you design the whole thing, right? And then you take that design, and then you need to come up with the steel. So it gets shipped off to a steel fabricator, okay? And that steel fabricator is, I guess we won't need to do that. I'm not sure if that's going to actually show by trying to show a video and record it and stuff like that. So we'll come back over here. So it goes over to a steel fabricator. And then the steel fabricator says, yep, this is how we interpret what your design is going to be. And then they give you these things called shop drawings. They say, this is what we're going to make, right? And then as an engineer, one of your jobs is to confirm that what they said, like what you wanted to happen and what the fabricator is going to provide you, are the same thing. And those things are called shop drawings. And many of you, if you do get jobs as being like interns or do go on into structural engineering, that'll be one of the first things that you get called upon to do, would be called upon to check shop drawings. And what you do is you look at your drawings and you look at the shop drawings from the fabricator and you make sure that they're the same. And if you look at that video somewhere anyway, you'll see that somebody's got a little highlighter out, and they're highlighting, and what they do is they highlight the structural engineering drawings, and then they highlight the fabricator drawings, okay? And then I guess, so then the fabricator doesn't actually make the steel members. The fabricator orders them up from a steel mill, and so a steel mill is actually what makes them. They're the ones that and actually I think that AISC touts this, and I don't know if it's mentioned in the video, but all wide flange sections and most structural sections in AISC, in the AISC Steel Manual, are recycled. That's one of the big giant positives associated with steel design, is the fact that it is recyclable, right? It's old cars, it's old stadiums, it's old buildings, right? And they take all that old steel and then they melt it down, and then they have a building product that's just as strong as what it's replacing or what it's recycled from. And so that I have to admit, that's one thing that's pretty cool, especially compared to concrete, right? Concrete, as they try to recycle it on occasions, but it's not the same thing as the recycling that comes from that. And so the mill makes these specimens, right? And they come out with this big giant bar. You can see it in the video. It comes with a big giant bar, and then that big giant bar, they heat it up and then they roll it. That's how they get those shapes. Is they have these big rollers that go back and forth on those bars, and it kind of, it's still hot in the process, and so I think you call hot rolled sections is what they're called, and they have this wheel roll back and forth, obviously under lots of pressure and stuff, and that's how they get those wide flange shapes and those channels and those angles, and that's why it's not like they're not taking two separate parts and welding them together to get the I-beams. It's all one cohesive unit. They're not casting metal into like a die that looks like a wide flange, right? They're just getting a big bar and then rolling it into those different sections, right? And so the steel fabricator will get these raw sections from the steel mill, and when they get those raw sections from the steel mill, they do the fabricating. And what do I mean by fabricating is they cut them to length, they put the holes in them, like if they're gonna have bolted connections, they go through and they drill the holes and everything, and they get it all prepped for shipping, okay, and ready and for construction, right? And I think the word that is used, and I don't like to use it, but it is erection, right? They prep it for erection, okay? That's the technical term that gets used in steel design. I am still a child. Every time I say erection, I giggle a little bit, okay? But I'm trying to become more of an adult. I'm gonna hopefully not continue to do that, and so it has this aspect to it, okay? Oh, and so anyways, so then they prep all these things at the fabricator. Then they take it from the fabricator, and they then take it and ship it to the job site, where then the iron workers, they are the ones that actually put together the structure, right? They bring it up, they connect all the elements and they make sure everything is flush, and they construct the whole building, right? And that's one of the positives, which we'll talk about steel design, right? It's everything's made in a factory and it shows up on the site, cut to the right length and ready to be built, right? And so a lot of times a steel structure will be constructed very quickly once it shows up on the job site, because you're just bolting a bunch of things together, or welding in certain cases and whatnot from there. A perfect example of one of a steel building that has recently been constructed is the town pump, or right next to the town pump. It's a new Bozeman Deaconess, like I think it's like a urgent care that's off of Cottonwood next to the town pump over there. And so if you're still in town and you drive by that, you can take a look. They just completed putting together the whole steel structure. Now, the other thing that they do historically, they'll put when they're done, when the iron workers are done constructing the building, and they have to come back and put the walls up and the floors and all that other stuff at this point. But when they're done with the overall skeleton of the structure, they'll put like a evergreen tree on top, like a Christmas tree on top. And if you go by that building that I was just telling you about, there is a little Christmas tree on the top of it to symbolize that the iron workers are done constructing that building. But and so if you watch that video, they show you little clips of all of that stuff happening, okay? As that's a lot of just my voice and no moving around and stuff like that, so I apologize. I guess I could have shown you me. So as I was giving you that little monologue, so take a look at that video if you haven't done so already. I think it's a really good resource just to kind of get you in the mood for steel design. Now, we're gonna go on and start talking about the design philosophy here, right? The design philosophy. My pencil's not working. Hold on. Get that working. Okay. All right, there we go. The design philosophy, right? And what I just mean by that is like what governs the design, right? Right? The design that governs this design, and it is AISC. AISC. right? Is the code that governs steel design, just like ACI, right? I guess I could have typed all this stuff. AISC, which it stands for. Oh, let me get this thing out there. American Institute of Steel Construction. Okay, they are the governing code for steel design. So we're going to use AISC. So that manual you got that you purchased, hopefully purchased and are ready to start using, is the AISC manual. Okay. You think with a special ability to draw straight lines, I could do it. I'm going to have some assistance. All right. And so what you're using, we're using the 15th edition of construction manual. It looks like a Bible, right? And then in there, we're going to show you in a little bit. They actually allow for AISC, or the ASD or LRFD. We are going to do LRFD design, load resistance factor design. And so let me show you. I'm going to give you a little tour of the code book, right? You guys have been dying to figure out how to use this thing. And so I think I could do this. I think I can do this. I think I messed around with this before. I am in my office. Turns out I'm an essential service, so I get to come to work. But not that I want to, but it works better here. I got really good internet access. My kids aren't here. Nobody else is on campus, right? And so I just shoot in here. I touch 2 doorknobs on my way in, and I close the door. And I'm kind of a germaphobe anyway, and so like right now, since I'm talking to you, I want to use my hand sanitizer that I have here. Like I'm gonna catch it from you or something. But I did, by the way, to give you guys some motivation to stick to your social isolation. I got an email from one of my dynamic students today who has asthma and is currently hospitalized in up at the Bozeman Deaconess, where he was hospitalized for a while. He is recovering now, but it is really close. It is in the community. It has been making it to students. So please practice social distancing, right? People are still getting together. I've seen it, but please don't do it. Okay, it's not worth it at this point. So, anyways, enough about that. So, your steel manual. Oh, look at that. It's like a mirror, so it's going to all be backwards here a little bit. But your steel manual. Let me give you a little rundown of it. It looks like a Bible. Looks really cool to carry around, right? It also has some other purposes as well. And so if you see on the side, it has all these little tabs. Well, I got my own tabs. I'm going to talk about those a little bit later. I think it's important, like, you should get ready to put little tabs in there, because there's just like with the ACI and code books in general, stuff is spread out everywhere in this book. And so it's kind of nice to come up with some sort of labeling system so you can kind of look up where you can quickly find some of the stuff that we're going to talk about in this class. And so that's what these tabs are, right? Is I've kind of highlighted certain areas, certain colors correspond to column design, certain colors correspond to beam design. They got a pretty good system. So if you see a practicing engineer, they have their steel manual and lots of tabs set up all over it, okay? But the other thing that's happening here is the code itself is kind of broken into its own thing. You got these little black tabs that are sitting here. And so there's kind of quick ways to get to different locations in this steel manual, right? And so I'm going to walk you through these a little bit and talk about it. The first one says dim. And hopefully you can pull out your steel manual and kind of play around with these things yourself. The steel manual under dimensions, okay, that dim stands for dimensions. And if you open it up, you find a lot of tables like this, okay? And what this is all of those sections, all the sections that AISC and fabricators and mills and stuff like that make. They're all right in here, okay? They're all located in this thing, and what you find in there is all these different variables, right? What the cross sectional area is, what the depth is, what the web thickness is, what the flanges are, what the width of the flanges are, and then some other, what's the moment of inertia, what's the elastic section modulus, what's the radius of gyration for all the different sections, pages and pages of all the different sections that are included in there, right? And these are going to be helpful for if we have to look up up certain properties and stuff of certain members and whatnot, right? Because remember, these things are made in a factory. You don't get to choose the sizes of them and stuff. Okay, and then you go on and you go through the general tab. I'm not exactly sure what's in the general tab too much. Let me look here. Oh, how to use the code. Oh, how to... The difference between LFD and ASD, a little bit of that discussion. Some general... It turns out there's a bunch of general information in here. What fee factors, tolerances... things of that nature, okay? And then it goes on, and like the next big chunk of these tabs, right? Almost the rest of the document are all these other ones. You have beams, columns, tension members, combinations, bolts, welds, connections, shear, and then PRC. I don't know what that is. Moments. I'm not exactly sure. A brace, components. So a lot of these things are design aids. This beam one right here is a design aid for designing beams. The next one is a design aid for designing columns. The next one's a design aid for designing tension members, right? It's not the code, but it provides these little tables. And throughout the rest of the class, I'll show you how to use some of these design aids. But it's just like, since everything's with concrete design, we had to pick the depth and the width, and we had full control over that. Now, though, we don't. And so now you could think about, you could have, if you're talking about the bending, you should just be able to say, I need a moment capacity of 150 kip feet or something like that. Well, since all the members exist, I should be able to look up what's a member that gives me 150 kip feet, right? I should just be able to look that sucker up, right? And in fact, you can. That's what these design, and where you'd find that would be in these design aids. It would say, like, I need to design a beam. I know my demand. What is the member that I need? Okay, and so it's looking up all those tables. So all these tabs are kind of structured around that, and so one is design of different elements. The other one's design of connections and things of that nature. Okay, and then you get to the back. Okay, and you get into this one that is called, oh, look at that. Just found a free couple coffees. Look at that. All right. That I tucked in there, I was using it as bookmarks. And so anyways, you get into the back, and there's one called SPEC, S-P-E-C. And what that is the specifications. Okay, what you see in the gray, about this much of the code, right here, about that much of the code right there is the code, right? It's the lawyer talk. It's this is how you calculate the capacity. This is like the ACI code, right? The ACI code doesn't have tables for capacities and stuff. It says, here are all the rules for calculating the capacities. This right here, the specifications part of this book is all those rules. These are the mechanisms of failure. This is how you calculate the capacities for these different members. These are how you calculate it is the rules. Okay, and if you remember, and then the difference between the white and so you can see there's white and then there's gray here. The difference between the white and the gray. The white. Okay, the white is there, and that is the code. Like, these are the rules. What the gray is the commentary. Is the commentary on the code. And if you remember in ACI, it was one column was the rules, and the second column was the commentary, a little discussion about what the rules are and why they're that way. And then ACI code's a little bit different. It's actually worse, right? Because you have on the front part of this, right, in this part is all the rules, and then if you want to say, well, what does the commentary say, you have to like flip back to where the tan part is or the gray part is and find the same section. So it's not as clean as what ACI does. The ACI's got the two different columns, and this has the front and the back. Okay, or it has the white and the gray, and they're kind of stacked in that sense. Okay, and so that's basically the rest of this AISC book. And again, as we move throughout the class through this semester, I'll kind of show you where we're going to be pulling stuff out of the specification. That's where the rules are. But then we'll also show you how to use the design aids, right? Because that's going to be really helpful to us, right? Because we're in the process of designing things, and so being able to take advantage of the design aids is going to be great. The design aids are based off of the specifications. How they came up with the capacities and stuff like that they use in the design aids come from the specifications, right? They use the rules of the specifications to make these design aids, okay? And so take a look at your book, kind of watch this video and kind of flip through through this thing at the same time. And kind of just make sure you know what's happening there, okay? let's see. Let's go back to this. Okay. And so, I mentioned that ASD for L and LRFD. It turns out the code lets you do ASD and LRFD. And, it's a little weird what happened, a little history behind it. Back in the day, AISC, I don't know, 20 years ago or so, they said, you know what, we're done with ASD, we're going straight to LRFD. And then so they did not allow ASD design. But what happened was a bunch of existing engineers that were all wanted to keep with ASD, they just kept doing ASD regardless. And what they did is they never upgraded their code book, right? They were on, I don't remember, it was like the 12th edition or 10th edition or something like that they made the change. And then what happened is they all stayed on the previous one. So if it was the 10th that came out with the new that got rid of ASD, they stayed on the 9th, and they were on the 9th forever. And then eventually the Steel Manual came back and said, or AISC came back and said, okay, fine, we're going to allow ASD. And so now this book includes ASD and LRFD, but we're going to stick to the LRFD. We're going to raise a new generation of people that want to do it the better way. Okay, because it does end up being better. Okay, so pros and cons. Let's talk a little bit about pros and cons. I don't know when I even started this, but we'll just keep going here. Pros and cons, right? There's lots of pros to concrete design. Steel design. I like to say that, concrete is way better and all that stuff. It is. I still think it's way better, but more durable, all those things. But then there are definitely some pros to steel, right? And I've mentioned a couple of them already. But one thing is it has good strength to weight ratios, really good strength to weight ratio, right? It is really strong compared to how, is steel heavy? Hell yeah, it's heavy. It's super heavy, right? But it is, it is super heavy. But then again, it also, it's also really, really strong, right? Yield stress is a typical section in this. Wide flange will be 50 KSI. And so it's incredibly strong relative to how much it weighs. Wood is on the other perspective. It also is a really high strength to weight ratio, except for it's light, super light compared to how strong it is. And so it has similar strength to weight ratios, whereas concrete is really heavy and not very strong. So there's no formwork, right? That's a definitely positive thing there. Constructability, right? It is fast, right? It takes you can put together a structure, construct a steel structure very rapidly. Okay, elegant connections. Right, that's an important one. Right, it's if you want to connect two elements to each other, right? Stick them next to each other and melt them together. Right, you weld them. Right, and or you have bolted connections. There's all sorts of connections, and it's pretty easy to connect steel elements. Where with concrete, no, it's pretty difficult. Right, you cast it all in one big specimen. You have all this steel, intermixed throughout, and to connect things, but it's not as elegant as connecting steel members. And I mentioned this a few minutes ago during my little dialogue there. Recyclable. Recyclable. Really? Recyclable? Recyclable. Okay, finally. I thought it would have been recyclable. Recyclable. Anyways, look at that. It's just now, it's trapped forever. It's trapped forever how bad of a speller I am. I can't even help with the help of spell check. So, 90%. That's what I have. I think that's the last member I have, that 90% of structural elements in AISC are recycled, right? Or made with the 90% recycled materials, right? And some of the cons, right? Some of the cons. It melts, okay? Right? It absolutely does, right? That's why the Twin Towers came down eventually, right? Steel is great, right? You hit the side of a building with this giant airplane, right? And the fact that it stayed standing as long as it did, magnificent. Okay, but it did eventually collapse, right? And it did so because that fire melts the steel. And in fact, you'll see also. I just get distracted because I teach a class that we discuss progressive collapse. And a few years ago, I was trying to look up. videos that talked about the collapse mechanisms and stuff like that were observed during the collapses of World Trade Center, and there's just so many videos saying that it's fake. Okay, and it is crazy. Okay, if you're looking for something to do while you're stuck inside, watch some of these like videos about how people think that the World Trade Center collapse was fake. Right? It is nuts, and that it was got big conspiracy theories. Like holy cow. Anyways, but it melts. That's one bad thing. The other thing it does is it rusts. Okay. Right, that's a bad thing, right? It goes through corrosion. It's susceptible to that. Back to the melting thing. That's the other thing that'll happen when you use steel in a structure. In certain parts of the building, they have to protect from burning, and what you just to make sure that you have a certain amount of burn time so people can get out of the building if the building starts on fire. And then so they have to put fire protection on these elements. And sometimes you're walking around. I do this a lot, but you're walking around inside of a structure, right? Look up and you'll see a lot of times it's like a steel member. It looks like the shape of a steel member, but it's coated in this like almost paper looking, like spray on paper mache type stuff. And that stuff you see right there is fire protection. It is something on there to protect the steel as long as possible so they can increase the amount of burn time it takes for the building to collapse so people can get out. And so sometimes you'll see that if it's in a critical area, like in hallways and things like that. So, and or stairwells and things of that nature. So it melts, it rusts, it's fatigue sensitive. Okay? It is fatigue sensitive. That is a problem. Concrete is not fatigue sensitive. Steel, right? If you have an element that undergoes lots and lots of repeated cycles, eventually that steel will break. Okay, it'll form these little fatigue cracks and then could fail. And so that's one of the negatives to it. And then the other thing is buckling, right? Buckling or stability. Right, and part of this, and we didn't really deal with this in concrete too much because concrete members end up, because it's not very strong, it ends up with really beefy elements. In steel, since it is so strong, you end up with these very slender elements. Right, and what I mean by that, it just means that they're really thin. Right, you have like a thin section. Right, you could instead of having to have like a 24-inch by 24-inch column with concrete, you end up with something that's significantly smaller because it's 10 times as strong. Right, and so you end up with something that's way less, and that becomes very susceptible to buckling. Right, or instability. I mean, just picture taking like a yardstick or something, push it on top of it, it'll buckle out and fail that way. And so that's one of the failure mechanisms that we always have to take into consideration when we're doing design is stability, right? That's going to be a new thing that we have to do through the design of most of our elements in steel design. Okay, so those are the pros and cons. I think that I hit a pretty comprehensive list there. There's obviously more than that, but that's all we're going to write down at this point, okay? So material characteristics, right? We have different types of steel. Okay, there's lots of different types of steel out there, okay? And then you'll see them, and we'll talk about these in a minute. Table 2-4 in the code, okay? And I think, do I have that below? The other thing I should note is that I've put the code sections. Oh, dang it. What am I doing? Oh, this is all one text box. Oh my God, how do I get out of this? Right. I put a lot of the code sections that follow here, right? You don't necessarily have to print these out if you're at home and you don't want to necessarily print these things out. You don't have to do it, right? I just included them here so the ease of when I'm lecturing and stuff like that. But all this stuff is in your steel manual that you have. If I have 2-4, I do not include it. All right, so I'm gonna bring it up. Thought I included it. All right, so you look at 2-4 in your code. All right. this is on backwards too. All right, I'll show it to you. So this is under the general tab. 2-4. All right, look at that. I got a little tab on it. All right, and so you'll see this. And so take a look at it in your code. It looks like it's on page 248, and it has all the different types of steel that are available. Okay, they have different grades of steel as you go down this column right here, and then it's actually worth discussing here for a little bit. So this talks about, like, if here's a wide flange section, right? You got this wide flange section, and it tells you what the typical type of steel a wide flange section is made out of. The black right here indicates the standard steel, and it's made out of A992 grade 50 steel down here, right? And then here are all the different types of steel you can get it in. If it's tan, you can get it in any one of these types of steel. These are all different types of steel going up and down. But then they also tell you what's the standard steel that it's made out of. Like, if you want an M section, it's made out of A36. If you want a W, it's made out of A992. But you can get it out of any of these other things, okay? And they have all sorts of fancy metals that you can use. You can make it out of. For various reasons, you might want it made out of different elements. And so if you look through that table, I recommend you doing that just to kind of see how that thing is structured, what the standard steels are, and things of that nature. You'll see that. Lost the piece of rebar there. You'll see that the different types of steel. So let's just go through a couple of those different types of steel. We have carbon steel. Right. This is A36. This used to be the standard thing that all wide flange sections were made out of. That is not the case anymore. A36 looks like a mess here. HSLA. So this is high strength, low alloy steel. This is A992, right? And that's the standard steel that wide flange sections are made out of at this point. We keep going with this list. This is going to be ugly. Down here. All right. They also make it out of. What do we got here? We got corrosion resistance. Right? In fact, they make stainless steel ones. I would love a stainless steel wide flange section. I think that would be magnificent. Okay, they have these. They have a bunch of them in here, quenched and tempered. Right? So what they do is they heat it way up, and then they dip it into water, and that's quenching and tempering it, and actually increase its hardness. Right. I don't know if you took material EMAT 251. I think they'd maybe talk about this stuff a little bit. And the idea behind it is you could fine tune performance. That's the whole idea, is that you can fine tune the performance of your steel member. Oh, that's what I did. There's the problem up here. There we go. What happened there? And so you can fine tune the performance of your steel, right? If you want it for a particular purpose, you use a certain type of steel, right? As the stress strain response, I just kind of already drew this in here for you, right? This is the same stress steel response of a piece of rebar. All steel basically behaves the same, at least the stuff that we use in structural engineering, besides pre-stressing steel. That has a little bit different behavior. But this value right here, so in steel, in concrete design, we use lowercase letters, but for some reason in steel design, we use uppercase letters. So that right there is the yield stress of the steel. That's F sub Y. This again, right here, is the modulus. That slope right there is the modulus of elasticity. That's still 29,000 KSI. Right, and then this one, my favorite, a pretty fun variable. This one right here is FU. Big capital FU, right? That ultimate yield stress. Okay, the other properties of steel that come up in steel design and different applications is the shear modulus, 154 KSI. Right, and this is the shear modulus. Right, if you load something up in shear, it's how much it displaces. It's a little more important in here than in concrete. And then Poisson's ratio is 0.3. Right, and that's how much, right, if you squish it, how much it bulges out, or if you pull on it, how much it gets sucked in, okay? So those are the properties of the steel. Okay, let's fill out this table, and we'll call it good for this lecture right here. But let's talk about the different shapes that you could find. Okay, there's lots of different shapes of steel, and we'll kind of fill out this table here together. So one of the top, or I guess one of the main, when you think of steel design, you probably think of this shape. Okay, this shape right here is what they would call a wide flange section. Okay, so these are the types we got. I think I might be able to type. Yeah. Okay, so these are wide flanges. Right? You think of it as being I-beams, but technically in this industry we call them wide flanges. And so there are different types of them. There's the W sections, there's the S sections, there's M sections, and there's HP sections. So those are your standard type members, or I guess, there's all of those things basically have that shape off to the left that looks like an I. They all have this shape over here. Okay, and then how are they designated? How do these things get called out? Well, how they get called out is, like, for instance, this would be like a W, or they'd be like this, W12. And I think you maybe talked about this in structures 1 a little bit. W12 by 57, okay, would be an example of how these things would be called out. This 12 right here is going to be the depth. Right, and this right here is the weight per foot, right, in pounds. Right, it's pounds per foot, I guess is what that is, right? And so, and what I mean by the depth, it's this height right here from out to out of this. Okay. And then, so that's you'll see those. And if it's an S or an M or HP, they're kind of all designated in a similar fashion. Now, the use of these things, this guy's beams and columns are the standard use of them. Right? Beams and columns are the main thing. And then the material that these guys are typically made out of is A992, right? And these guys have an FY of 50 KSI, right? But you can get, if you look at that table, you can get wide flanges and M's and stuff like that, and all different shapes and size, all different materials, right? And so you can get all sorts of different materials, but your standard material, most likely you're going to get a material of 50 KSI. Now, when we talk over here about what these guys are called angles and double angles. Okay. The angles and double angles, and a lot of times they're designated with an L out front, right? And we'll talk about the designation in a second. So when I show the dash right here, when I show this dash, this would be a double angle, right? And actually, it turns out when you look in those dimension tables and stuff like that, they give you properties of just a single angle and double angles in some cases. If you're looking if you're designing double angles, they'll give you the properties of two of them together. All right, and so those are pretty standard, these double angles. They're two separate members, but you get to treat them as one during your design and stuff like that. So then, how are these things designated? L3 by 3 by 1/2, for instance. Okay, and as you may be able to deduce yourself, right? These first two numbers are the dimensions. Right, dimensions of the legs. We're going to do an example a little bit later with these guys, but these guys are the dimensions. Dimension of the legs. Right, and this guy right here is the thickness. Right. So a 3 by 3 would have a 3-inch leg going one direction, a 3-inch. So this would have 3 by 3 by 1/2. It would be 3 inches by 3 inches, and then the thickness of this guy right here, right, the thickness of this plate, if you will, would be 1/2 inch, right? And so that's how those things get called out. Okay, how are these things used Right? These guys get used for bracing and tension members. Right? They don't get used. They're very slender. They don't get used for bending elements. They don't get used for columns very often, right? And for various reasons. But that typically they'll get used for bracing and tension members. These guys are typically made out of a 36 steel. Oh, a 36. Oh my gosh. All right, that's fine. A30. Oh, you can actually see me typing probably, right? A36 steel. Whereas FY 36. Okay. Yep. Okay. So let's keep going with this thing. These guys down here are called channels and double channels. Channels. Okay. Channels and double channels. They're designated with the big C out front. Okay. How do these things get, or they have a C in there. How do these things get called out? Well, we'll call it C15 by 50. Okay. And that same idea there, that's depth. I don't like that. I'm gonna put a little X. Depth by weight. Right. Just like a wide flange gets called out. Okay, and these guys get used, same idea. They get used as bracing and tension members as well. And they are made out of a 36 steel as well. Okay? And again, just like with they have properties for double channels as properties for single channels. This guy I think is pretty interesting. One of my favorite sections. This is a T section. Okay. And they made by cutting wide flange in two. Right? So that's what they do. They just take one of these wide flanges like this, one of these guys with these wide flanges like this, and they cut that sucker in half. Right? They cut it in half, and what do you get? You get a T when you cut the I in half. Okay, and so they get designated a bunch of different ways, or they get designated in a similar fashion. Right? So these guys get called out with a WT. So that just means it's a wide flange section, a W section from up above that gets cut into a T. And so this is like 16.5 by 76, and again that's a depth versus a width, or weight, sorry, depth versus weight, or depth times weight, I guess. These things they get used for columns and bracing. It's kind of the standard application of those guys, and these are made out of A500. No, wrong one. These get called, nope, these, goes down there. This is the same, and this is the same. Obviously, this is going to be made out of A992 steel as well, right? Because it's going to be made out of the same, it's going to be made out of the same thing that the wide flanges are made out of, all right? These guys down here, these are called HSS sections. Hollow structural sections, right? Hollow structural sections. They come in circles or they come in squares. All the squares come in. All these squares are called HSS, hollow structural sections. Right, HSS 14 by 14 by 5/8. Right, that is dimensions, dims by thickness. 14 by 14 is 14 wide, 14 high, and then it is 5/8 of an inch thick. And so that would be here, right? 14, and that would be 14, and then the thickness would be that thickness of the plate there. And so those are just steel squares or rectangles and stuff like that. Those guys get used as column and bracing. These guys are made with A500. Grade B. Okay, and then these other ones, so again, you can have them in rectangles and squares, but you can also get them in circles. Okay, and these circles right here, these guys, there's actually two ways. You can have HSS sections and you can have pipes. It's kind of weird, right? But you have a pipe that's designed for something else, but technically those pipes can be used as structural elements as well. And so in the steel manual, they have HSS sections and pipes. Both are circles. Okay, and then the designation, I'm just going to say it depends. Are you calling out a on HSS versus pipe? right? Depending on which one you're calling out, it might be a different designation there. Right, and then these guys get used for columns and bracing as well. Right, and these though are made out, again, depends. Right, and that'd be table 2-4. We'll talk more about that. And all of these members over here, if you look at that T-4, you can kind of see where those types of steel and stuff like that came from. All right. So then with that, okay, that's kind of your introduction to steel design, right? And that's including watching that video. I do highly recommend watching that video. And then what we'll do with the next lecture is talk about tension member design, okay? And that's where we'll start diving in, and we're going to introduce this idea of limit states and how do you calculate the limit states. Then we'll do flexural members. We'll do bending in steel members, and that takes most of the time, and then we'll do columns, and then that's it. We're done after that point right there. So hopefully everybody's staying safe. Hopefully these videos are helpful, and we'll go from there. And like I said, stay tuned. I'll make some sort of announcement for maybe tomorrow at 2. We'll do some sort of review session for the take-home exam on